All right, so we come to the last applications of probability generating function, right? Now, this subtopic is called the sum of independent random variables. All right. Now, I'm going to quote one example from the textbook here. Okay. Now, you have seen the result, the result of the performance of a certain football team, okay, throughout the season. And then you have also seen the result of the performance of Team B over the same season also. So let's assume that these are all the result recorded relevant to Team A and Team B over a certain period of time. Okay, so here you can see that Team A, the number of score or number of goals set by Team A, okay, um, are shown here. So you can see that they don't have score for 149 times. Chances of not scoring is 0.323 here. So it seems like the team B is doing much more better than team A based on the raw result here, right? And then the total numbers of games that they have played throughout the seasons is shown here, right? And then your respective probability are given here. Now, bear in mind, this probability that they have recorded may not be modeled using a standard probability distribution, or it may fit nicely with some standard probability distributions here, right? But our concern for today's section is more towards the independent random variable, right? Now, what we are going to develop later, I'm going to show it to you shortly, right? Now, first of all, let's try to recap for Team A. Okay, for Team A, if we use the X, okay, so if I say that X represent number, I would say X represent number of goals achieved by Team A, okay, whereby Y represent number of goals achieved by Team B here, right? And then we make one assumptions that the result obtained by Team B does not affect the result or the performance of Team A. What actually affect their performance is mostly their trainings and then their strategy and so on and so forth. So indirectly, Team B does not affect the result of Team A, nor does Team A affect the result of Team B. So therefore, we make assumptions that X and Y, the event of X and Y are independent, discrete random variable. So they are independent here, right? And then to recap on the probability generating functions. So for Team A, it has its own probability generating function. So therefore, I'm going to write it down. So for Team A, Team A, sorry. Team A, I might as well write GA then. GA or GX? Okay, maybe I'll use GX then. So I use GX to represent the probability generating functions for Team A, uh, T here. Okay. And then that will be given by all these probability here, or I could write it down in a more general form. So take for instance, I can write it down is actually x equals 0 plus px equal to 1 t px equal to 2 t square and px equal to 3. So I have 3. This is 0, 1, 2, 3, 4, 5, 6. So I have 5 actually. So P equal to 4 P equal to 5. All right, because 6 does not have any probability. Now, there you have it. That is the general representations of the probability generating functions that represent the performance of team A. Whereby for team B, its probability generating functions are labeled as GY then would be given by instead of using X because this is Y now, so that is Y equals 0, PY equal to 1. Okay, Y5, let's see, 5, 6, 7. Okay, it go up to 7, so you have PY equals 6 and PY equal to 7 here. All right, now those are the probability generating functions that represent performance of team B there. All right. Okay, so I hope that's clear. All right. Now, there will be time when ones might be interested to ask this question. Okay, what would be the probability of the total goals, okay, obtained by team A and B that is equal to 3, for instance? So there will be a question here that might be interested by someone or raised by someone in this case, what would be the probability of the sum of the goal um, collected from team A and B is actually equal to a 3, for instance. Okay, so how do we actually work out the probability of the sum of the goals achieved by team A and B equal to 3? So how are we going to work that out? By using the combined probability generating functions. Okay, so how are we going to do that? Before that, let's try to understand more what we are referring to here. So probability of sum of x and y equal to 3 basically mean it could means px, the team A is not scoring any goal, and at the same time team Y has already scored 3 goals, so their total number of goals is actually equal to 3. Or it could be team A has already scored 1, but team B has already scored 2, therefore their sum of their score is a 3 there. Or it could means probability of X scoring 2 goals, but Y has achieved 1 goal here. So in general, there are total of 3 goals uh, achieved as a whole, right? Or it could be, lastly, X has achieved 3 goals, but Y does not achieve any goals at all. Right. These are all the one, two, three, four possibility of the result that will yield the sum of goal equal to a 3 here. All right. So I hope that you are clear at this point. Later on, we are going to look at how we are going to make use of probability generating functions, the combined probability generating functions between these two random variable x and y to obtain or to answer this question here. We're going to make use of the combined probability generating functions to answer these questions. All right. Okay. We're going to come back shortly. I'm going to rewrite this in a proper manner. Then we can understand it more easily. Then we can go through the derivations as to how we make use of the combined probability generating function, right? All right, welcome back. All right, now I'm going to rewrite a more general probability generating functions that represent the result obtained by team A and team B here. So the first one is given by GX, probability generating functions that represent the performance of team A. I try to write it down in a more general form. So I did not actually specifically write up to how many probability involved, like in the table just now. So I try to write in a more general sense. So we can have probability up to x equal to m here, whereby for team B, the probability could run up to n here, for instance. Now, both of these probability may not be, the number of probability may not be exactly the same in this case, right? Okay, where m and n, okay, where m and n are all uh, real integers number in this case, right? Okay, so I hope that is clear. Now, from here onwards, we're going to try something here and then to see whether we can discover something new here. So we're going to multiply, okay, we're going to multiply the probability generating functions between x and y in this case. Okay, now it's a very lengthy process here, so bear with me. Okay, so if we multiply with that, we will get something like this. It'll be the whole expression multiply each other, so we have to expand it. And now the expansion will look something like this. It's a 3 here. Hold on. Okay, sorry for the delay here. Please wait for a while. Okay, so 3 here. And so on and so forth until we have. Alright, now the first expansion will look something like this. Multiply by py equals 0. Okay, so that's the first expansion. And then, of course, we're going to continue on with the second expansion here. Right, now the second expansions will be this. Shouldn't be a tough process to work on. It's just that it's a bit tedious. You can see that it's a repetitions of the first organization in this case. Okay, now that will be my second expansion. That would be py equal to 1 t now. Okay, I hope that you can see there's a t there. And then, of course, I'm going to expand it further so that you can see this more explicitly. Uh, Now, writing out this one really require patience. Okay. All right, now that will be the third expansion. We will have py equal to 2 t squared. And then, of course, we're going to add all this up, okay, up until we have this. Right, up until the last term, which is py equal to n t to the power n. And then there you have it. Those are all the expansion when we perform the multiplications between the two probability generating functions here. Right. Now, what I want you to observe next is very important. Okay, now you can see that from here I can quickly extract. Okay, I can quickly extract P0 multiply with Y0. So Px0 multiply with Y0. All right, now that will be a standalone term. Okay, but what come next is you will see that there is a t term. So this py equals 0 with px equal to t would yield the expressions with term t. Okay, with term t here. Right. At the same time, we look at the second row. The py equal to 1 multiply with this one would yield the same term also t. So therefore, these two terms we will have to join them together. All right. Okay, I hope that's clear. So that's how we join them together. And then you will notice that, right, now you will notice that as we go along, okay, for the term with T2, it will also join with this term here. So T2 you will join with this. Okay, so I'm going to write down the term T, T first, the term with the T. So I'm going to write this one down as plus. All right. So for T we have P x equal to 1 multiply with T and then multiply with Py equal to 0. And okay, and at the same time I have Px equal to 0, Py equal to 1, a T. Right. So that's it for the term T. Those are only two pairs that produce a term T here, right? So we don't have any other pair. Now we are done. Now next we're going to look at the pair that produce term T square now. Okay, so for T square, if you look at T square itself, I will have Px equal to 2 T square multiplied with y equals 0. Or okay, or I'm going to join it together with like if you see that the second one will be this one here. Okay, this one multiplied with this, and don't forget this pair also join with this one here. So there are three pairs this time that produce T3 there, right? So maybe it's best if I write it down below there, then you can see the combinations more clearly. So from here, that will be the same as x equal to 2, t square py equal to 0, or it could be px equal to 1, t, py equal to 1, t, or it could be px equal to 0, and then py equal to 2, t squared. Right. So I hope that is clear at this point. Just check through if we miss out anything. Now, therefore, that is your second term. Of course, you can continue to perform all this summation until okay until we reach the last term, of course, right? Until you reach the last term. So the last term is this one here. So I'm gonna write it down. So the only last term that we have is here. That will be px equal to m tm py equal to n tn. Right, now that will be our last term in this case, right? So I hope that is clear at this point. Now, after that, I'm going to rewrite it neatly this time so that you can see it more clearly. So I'm going to use the same color pattern here so that you can recognize the term. All right, so that's the first term. And then for the blue one, we can rearrange it in such a way that it looks something like this. You can see that there's a T. And then next we have the green one. So the green one, we have Px x equal to 2, py equal to 0, or x equal to 1, py equal to 1, or you see that this is actually t squared. And then, of course, lastly, we will add up with the last term, which is xm py equal to n, and then t m plus n. And then there you have it. All right, now do take your time to actually look through this expansion, okay? Because what come next would be very important here. All right. Okay. Now I'm going to pause here for a while. Bear in mind, I'm going to make use of the last result here. So I'm going to bring it back to the top. Later on, we're going to further analyze it. What is the further properties that we can derive from this, right? Stay tuned. All right, this is where we are. This is the result that we have obtained. I just try to reorganize it back again. Okay, okay, this is how it look like. Yeah, do take a few minutes just to look it through again, compare the answer that I have and the answer that you would get. Right? Now, from here onwards, we can actually rewrite this form um, in a more implicit format so that we can tie it to the combinations of probability generating functions. And then how would that look like? We're going to check this out. Right? So for the first one, we can actually write, instead of writing the multiplication here, I can actually write down x plus y is actually equal to 0. You can see that the sum of your goals over the season is actually equal to 0. And then the second one here, I could have written that down as uh, implicitly as x plus y. Your sum of your goal would be equal to a 1 here. So there are two possibilities here. And then this stay with t. And then next, for the green one, I can actually write it down as the sum of the goal, which is equal to a 2. So in this case, it's t squared. And of course, lastly, I can write this as p x plus y is actually equal to m plus n here. T raised to the power of this. Right. Now you can see that that is how it looks like in this case. This is a more explicit form, and then we can convert it into a more implicit form at this point. Right. I hope that is clear at this point. Okay. Now from here onward, you will see that this is yet another probability generating function. Okay, we can actually write this as this is the same as tx px plus y. Is it px plus y? Let me see. Yep, correct. So px plus y is actually equal to the certain sum here. So here I'll write it down as let me see. Yep, that will be equal to x. Should I use x here? It'll be, yeah, maybe I should write as x plus y then. Okay, it should look something like this. So let me check that out. Yeah, I don't think I want to use x here. It might be a bit okay. Never mind. I'll stick with the x here. So in this case, you can see that this can be written generally as tx. I'm just trying to generalize the pattern here. You can see that the x start from 0 in this case, okay, until m plus n here, until m plus n. So that's how it actually look like. Okay, and then you will notice that this is very similar to another probability generating functions here. So this one we can actually write it down as gx plus yt. Okay, so this gx plus yt is the combined probability generating functions for both of the independent variable of x and y. Therefore, we can conclude that the sum of the probability generating function is the same as the multiplications of each individual probability generating functions here. Now, this is the main result that we are interested to use shortly. Okay, so I hope we are clear with this. So you can see that gx is given by this, gy is this. So when you combine them, that is actually the sum of the probability. So therefore, we can write down a combined probability generating function. If you combine the sum, it will be the same as the product of the individual probability generating functions. So let me rephrase again. The sum of their probability generating function is the same as the product of their individual probability generating function. Provided, of course, provided both the x and y events are independent in this case. Right. So this is the main result here. And then, of course, finally, you can further extend this. In the future, you can further extend this to cover three events, not necessarily one event. So we can actually have like the sum of three events would be the same as the products of all their individual probability generating function. Example, it could be something like this. All right. So we're going to check out later how are we going to make use of this result that we have derived here, right? So stay tuned on this. All right, example number one. Let's try to look at how do we apply the sum of the probability generating functions as the product of their individual probability generating functions. Okay. Now, a discrete random variable x having a discrete values from 0 to 2 has a probability generating functions given as such, and another discrete random variable y having a discrete values from 0 to 1 having probability generating functions given as gy. Okay, now assume that both the x and y events are independent. Therefore, we're going to find the probability generating functions for the sum of their um, discrete random variable gx plus y. Okay, let's look at this. Okay, number one. So gx plus y here. Right. Now we have learned that from our previous derivation. The sum of the probability generating function is the same as the product of their individual probability generating function. Okay, so it's their product. Now we're going to make use of this by taking in whatever that is given to us. That is 14t plus, and then gy is given by this. Okay, you can see that that's what we have currently. Okay. Now, of course, you can do the expansion as you like. So if I expand it, I would get like, what do I have? I have 1 over 6 over 12t. I will have 1 over 6t. Then after that, I'll have 1 over 12t square. And then after that, I have 1/3 of t square. And then finally, I will have 1/6 of t6 there. So I should have 6 terms in this case. If you try to remember how many terms you should have, here you have 3 terms, here you have 2 terms. So the total number of possibility that you should have will be 3 times 2. You should have 6 or 2, 4, 6 there. Yeah. And then of course we can simplify them. I just have one constant here. I have two sets of t, two sets of t square. Now that would be, if I try to simplify that, 3, that is 1 over 4t. And then this one 4 is, let me see, 4 is 5. 5 over 12t square. And then lastly I have my 6. Okay, so there you have it. The sum of a probability generating function given as such. Okay, now second question. Show that the expected discrete random variable x plus y is the same as the sum of that, and then the variance is equal to that. Okay, now we're going to try to check whether it works or not. All right. Okay, now first of all, now for this one here, okay, ex plus y. So let's start from here. All right. Now this is actually given by now just to recap, is given by the first derivative of, because we're dealing with the sum of expected values, so therefore it must be the sum of the probability generating function first derivative, and then substitute the value of 1 here. So I hope that is clear. Okay, now all we need to do is to differentiate these ones. I'm going to differentiate that. You will have a 1 4 plus 5 over 6t, and then 1 over 2t squared there, right? And then substitute the 1 into the t there, into the function, sorry. We would have 1 4 plus 5 6 here, plus 1 2 there, right? So let's see what do we have here. So 3 8, so that is 4 3, so 4 3, 16 19, 4 3 19, so it's 19 over 12 there. Right, so I hope that is correct. And then therefore the mean for the sum of x and y must be equal to 19 over 12 then. Okay, right. Now just for checking purpose, okay, I just need to make sure that I got the correct value here. So just let me quickly check it out. Hopefully I got the correct number. Right, yes, it is. So it's 19 over 12 there. Right, now I hope that is clear, the first part. Okay, now the second part, uh, we have proven the left hand expression. Now we have to prove the right hand expression there. Getting the right hand expression shouldn't be a problem in this case. Okay, now first of all we have gx here, which is given by this. So therefore, the first derivative of this, first derivative is equal to 1 4 plus t. Okay, and then by substitute t equal to 1, our first derivative would yield 5 over 4. Okay, we're going to repeat that for y also. So y is given as such. So here I'm just going to differentiate directly. That will be a 1/3. Therefore, there's nothing much we can do here. So the first derivative, by having t equal to 1, must be 1/3 then. Okay. And then the sum, so ex plus ey here is the same as the first derivative of x and the first derivative of y. Okay, so I hope that's clear. From here, we have already obtained the numbers here. 15, 19. So it's actually 19 over 12. Yep, which actually matches this. Therefore, we can conclude that, yep, so the sum of the expected value is the same as the sum of your individual expected value. Of course, given that x and y are independent, right? Okay, so I hope that is clear for the first part. Now, next, I'm going to clean this up and then I'm going to show you the last sections here. How do we verify the variance then, right? All right. Okay. Now, these are the result that we have obtained previously. We have found the first derivative for our probability generating functions for x and the probability generating function for y here. Okay. Now we're going to proceed on by differentiating this one more time. Now that would be a 1, of course. And then for this, it will be 0. So these are the result that we have obtained currently. Now we're going to work out the variance. Okay. Now for the variance of x plus y, that must be the same as, okay, now I've forgotten to write down the result for this. Okay, what was the result? Let me see. Okay, hold on. Let me try to recall. All right. So after checking, now this is the combined probability generating functions between x and y. Okay. Now that will be given by, for variance, it will be given by the second derivative of 1 here, x plus y. And then we have to have the first derivative, x plus y. And then, of course, we need to have the first derivative, x plus y, or 1 here, a square of that. So now, let's try to differentiate this one more time here. So the t must be the same as quarter 5 over 6t, and then finally 1 over 2t squared. Okay, 3, 1 over 2t squared. Let me see, 5, 6. Okay, there you have it. And then don't forget we need the second derivative. So second derivative will be 5 over 6, and then a t. Right. Now, what comes next would not be tough. All you need to do is just obtain the evaluations of x plus y by letting t go to 1. So we can just substitute t go to 1 here. Let me see what do we have here. 2, 3, 3 over 4. So we have 3 over 4 plus 5 over 6 there. 3, 9, 2, 10. So this one will be a 12 then. Okay, 3, 2, 3, 9, 2, 10, 9, 10, 19 over 12 here. All right, now that's correct. You can help me to check along the way. Now that will be the first result, and then the second result will be by letting t equal to 2, substitute that into the second derivative. Okay, so by putting 1 here, that will be easier. 11 over 6 then. Okay, now once we have done with that, all we need to do is just substitute this result back into equations number 1 here. Therefore, our variance, the sum of the variance, is actually equal to, what do we have here? 11 over 6 plus this one is 19 over 12. And then finally, I need this result one more time, 19 over 12. Okay, now let me take out my calculators faster in this case. Okay, 11 over 6 plus 19 over 12. Subtract off with 19 over 12 squared. Is that correct? Yep. Now, therefore, the variance will be equal to, maybe it's best if I just keep it as 131 or 144. But if you like to keep it as a decimal, Yeah, we may have to compare the decimal up to a certain um, significant figures. So take for instance, we leave it as 0.9097 here. Okay, so I hope that is clear up to this point. Now, lastly, we just need to verify the sum of the individual variance there. So for variant x, variant x is the second derivative of x here, the first derivative, sorry, of 1, and then subtract off with first derivative square. So the first derivative that we have, what do we have here? Now all you need to do is put in the second derivative of this. Okay, so if I put a 1 there, it must be a 1 then, in this case. And then for this one here, if it's a 1, it's a 5 over 4. And then I need to subtract that with 5 over 4 square there. So that will be a 9 over 4. And then with 25 over 16. Okay, let me see. 36 there. So 11 over 16. Is that correct? Let me check. 36, 11. Yep, correct. Right. And then as for y, variance for y, we also do the same thing. Y, this is x. I forgot to write that down. Okay, this is 1. Okay, so the second derivative for probability generating functions for y. So y is here, second derivative is 0. The first derivative is 1/3, and then minus 1/3 square there. And then therefore this one will be 3, 2, 2 over 9 then. Let me check if I got it correct. This one was 9, 3, 2, 2 over 9. Yep, correct. Therefore the sum of this will be 11 over 16 plus 2 over 9. Okay, I also need to take out my calculator just in case. Okay, just let me try this out. 11 over 16 add up with 2 over 9. And then that actually yield 131,144. Yep, so 131,144. 144. And then yes, therefore we can conclude that variance, the sum of the variance must be the same as the sum of its individual variance x and y. And then that complete our proof here. All right, I hope that is clear. We're going to move on to the next example shortly. All right, let's take a look at the second example. All right, so here we have to find the probability generating function for the total number of sixes when 5 fair dice are thrown. So here you have to quickly recognize that this is a binomial distribution. Okay. Now, knowing that this is a binomial distribution, you have to identify some of the parameters relevant to binomial distributions. Okay. Now we will label x represent number of number of sixes of 10. All right. So from here, we know that the probability of success of getting a 6 is actually 1 over 6, making assumptions that this is a fair die, 6 faces. All right. And then it is a binomial distribution. We have a number of trials of 5. Oh yeah, in this case, I write down number of trials 5. And then probability of success is 1/6. Also know that Q is actually equal to 1 minus P, which is 5 over 6. Yeah. So we try to write out all the properties relevant to binomial distributions here. And then we also know that the probability generating functions, okay, probability generating functions for these binomial distributions. Just for binomial distribution itself, let me see total number of sixes. You can have one, six. Okay, so total number of sixes here. So in this case, I will write down the probability generating functions for um, just for one die. Okay, I forgot to mention that this is a number of sixes obtained from a die itself. Okay, so um, when five fair dice are thrown. Okay, so how many six are we getting here? So we have, okay, if you still remember, is given by q plus pt to the power of n here. Okay, now therefore that is a 5 over 6. We have p, which is 1 over 6 here, and then to a power of 5 here. All right. Okay, so from here, of course, you can simplify this. So take for instance, that will be 6 to the power of 5. Wow, there's a very huge numbers there. So let me get the number. I also can't remember this number here. Okay, 6, um, 5 of them, right? Yeah, correct. So that is actually 7, 6. Okay, so 5 plus a t to the power of 5 there. Right? So I hope that is clear. We're going to move on to the next section. All right. So I have checked the value. Everything is correct. Okay. Now you may be wondering what is the connections between this and the sum of all independence event in this case, right? Now, just to give you the uh, the connections here, right? Now, first of all, the generating functions, the probability generating functions for one die itself, just for one die itself, is actually given by now I would say G1, just one die itself, is given by 5 over 6 plus 1 over 6t only. That's just for one die. That is the probability generating functions for one die. Uh, it's either you don't get it's either you get no 6 or you get a 6 in this case, right? Now, therefore, the total number of sixes. Okay, we are talking about total number of sixes. There are uh, five die here. Right, so five fair dice here. So therefore, we are actually adding up all the independent fair dice results. So it's actually 1, 2, 3, 4, 5 here, which is exactly the same as GXT because they are all independent. 1, 2, 3, 4, 5. Okay, there you have it. Those are the five. Right. Okay. Now, in this case, you can, of course, simplify it to the power of 5. That's what we have obtained, actually. Right. So this is the connections between the sum of all the probability generating functions. Of course, generally we don't actually see in this way. So we could have just obtained it directly in this way, right? Now, once you have obtained that, getting the mean and variance shouldn't be a problem here. So all you need to do is just get the first derivative here. So the first derivative is just 5 over 776, 5 plus t to about 4 there, right? And then therefore we can actually get the value by letting t equal to 1. That will be a 6. Okay, that is actually a 6. So let me see here. Just now this is 6, 5 here. So if you put a 1 here, this is 6, 5. this is 6, 5. This is 6, 4. So only left with 5 over 6. Alright. And then we're going to perform the second derivative also before we try to finalize the answer. Now the second derivative will be 20 over 7776 here, 5 plus t raised to the power 3 there. Now, of course, the second derivative by letting t go to 1 here, that will be a 6563, so that will be a 36 then. So 20 over 36, or yeah, or 5 over 9 there. Therefore, at this point, we can try to finalize our answer now. Okay, so at this point, we're going to obtain the mean. Okay, so this is the summary now. Okay, so to get the mean, we can obtain it by using its first derivative. Okay, which we have already obtained, 5 over 6, and then its variance is given by this formula one more time, so I'll write it down again. Okay, so therefore we have 5 over 9 here. We have 5 over 6, and then finally we have 5 over 6 again. Square. Okay, I think it's better if I get my calculator here. It will save a bit of time. We don't have to worry too much about its accuracy. I assume it should be correct. Okay, so that will be a 5 over 6, and then minus of 5 over 6 to a power of 2 there. All right, so that will be that will give us 25 over 36. So 25 over 36. All right, and then there you have it. How do we make use of the probability generating functions to obtain the mean and the variance using the first derivative and the second derivative? And then indirectly, I have shown you how to apply the sum of probability generating functions using the product of its individual probability generating function. All right, so I'm going to move on to the last questions for today. All right, let's look at our last example today. Now, Gina regularly practices archery. Now, the probability of her hitting the goal, the center of the target, with any arrow is 1/3. Now, we need to find the probability generating functions GT of the number of shots until she hits the goal for the first time. Okay. Now, before we start with this, we have to label what does the X actually represent. So, X represent the number of shots. Okay, so I will label this as number of shots um, up until she hits the first goal, right? And up until she hit her first goal, right? So there's X. Now we know that this is a geometric distribution, so therefore we can represent this as a geometric distribution with the probability of success already has been given to us, which is 1/3 here. So probability of success is 1/3. Probability of failure is 1 minus p here, which is 2 over 3 here. All right. Now I hope that is clear at this point. Okay. So from here onward, okay, now what we need to do now is we have to recall the probability mass function. The probability mass functions for geometric distribution is given as number of failures up until, and then a number of success here. All right, so that's the formula for the geometric distribution. Okay, now next we have to find the probability generating functions for this geometric distribution. Okay, so the GT, okay, GT is actually given as the, if you use the definition is here, so that would be the same as the TX 2/3 x minus 1, 1/3. All right, so the sum there. But you do notice that the probability generating functions for any geometric distributions can be written as such pt over 1 minus qt there, all right, where the probability of p is given by 1/3, and then probability of q is 2/3. And therefore, if you try to simplify that, we will be able to get t over 3 minus 2t. And then there you have it. The probability generating functions that represent number of shots until she hits the goal for the first time. All right. So I hope that's clear for the first one. I'm going to show you number two shortly. All right. Now let's take a look at the second question. I just written this down for reference here. Okay, second question. Now, show that the probability generating functions of the number of shots until she hits the goal for the second time now. Right. Now, these distributions may not be familiar to a few of you. I will try to provide an extra videos to explain what sorts of distribution is this. This is what we call as the negative. We call this negative binomial distribution. Okay. Now, negative just simply means that number of failures occur before the person managed to achieve the first success or the second successes here. Right. So this is called the negative binomial distribution, or sometime in the statistic literature, it's called the Pascal distribution. Right. And then we are going to label the discrete random variable. So y represent number of shots, okay, until she hits the goal for the second time. All right, now that will be our random variable. Now the probability mass function. The probability mass functions for this, okay, here I just simplify that, is given by this one here. So let's label as R instead of using X in this case because we already used that X in the previous example. It's given by this formula here. Okay, so that will be like 1/3. Now she managed to hit the goal for the second time, so this is where the second actually come in. But she will have to fail for this number of time. So this will be the number of failure involved, right? Now you can see this explanation in the separate video in more detail, right? So from here, indirectly, you can simplify that as now it's quite obvious. This combination is basically just this. Okay, so there you have it. There's a probability mass functions. Now we know the probability mass function. Uh, we can actually produce or construct the probability generating functions for this second event. So we're going to construct this gy now. Okay, now how to do it? The same idea here. So we will use the same method like before. So that will be from tx r1. Oh yeah, tx here. Sorry. Okay, let me correct that a bit. So it should be tx r minus 1, 1 over 9, basically. Okay, and then this is r minus 2 here as a sum of all this. Okay, so if I were to do this explicitly, it will look something like this now. Okay, I try to take out as many variable as possible in this case. So we can actually take out like the 2 over 3 here. So that will be 9 over 4. 9 over 4, so that will be actually 1 over 4. If I simplify that, that will be 1 over 4, and then I will have the tx. Let me see here. Am I using an x or r here? Okay, this is 1, 2, 3. Okay, because this is r. Sorry, my bad here. Because it's r, so I should be using r here. So you might want to get used to this notation here. So there should be a r, and then yeah, because the r start from 1, 2, 3, and so on and so forth. Therefore, if I simplify this, I will get tr r minus 1. The 1 9 is gone, so I will only have 2 power r here. Okay, so generally that's how it actually look like in this case. Okay, and then the r itself, I can also actually take it out, right? So, but anyway, I can write it down as this. There's 1 over 4. When r is equal to 1, so when r is equal to 1, sorry, the r actually start from 2, sorry. I need to write that down. R is supposed to start from 2, not 1, 2, 3, and so on, because for the second time there. So supposed to start from 2. Therefore, we're going to start from 2 here. It will be T2, 1, 2 to the power of 2. And then after that, 3. So T3, that will be a 2, 2 over 3 to the power of 3. And then after that, a 4. A 4. I think I wrote, oh yeah, yeah, a 4. So that will be a 4 there. And so on and so forth, of course, until infinity here. Okay, so from here we can factorize the we can actually factorize the 2 over 3 here. That will be 4 1 over 9 then. So that will be 1 over 9. I can also take out the t squared there. Okay, so that will be a 1. And then I have took out the 2 over 3, so only have 2 over 3. Therefore, there will be a 4 4 over 3. So I have taken out that. And then after that, what do we have here? I have taken out that 2 there. So that will be, let me see, 4. So that will be a 4 over 3 also. Then I've taken out that. So t square, t square, and so on and so forth. All right. Okay, so that's what we have currently. Okay, I'm going to continue in a while. So please remember this is the result that we have. All right, so here I try to copy back the probability generating functions for y that we have obtained previously. So just try to write out as more terms as before. I think we need more terms instead of the 1, 2, 3, 3 terms just now. So I add on one more terms here. Okay, so please refer to the latest one here. Now from here we can again, I'm going to repeat the same process again. We're going to factorize that out. If you factorize that out, you will get 1 over 3t square. Yeah, we will be able to obtain 1 over t square here. And then we're going to take out everything out here, and then therefore this will be a 1, and then this would only be 2, and then we have already taken out 2 here, so therefore you're only left with um, 2 over 3, okay, t here. Okay, so that's what we have. And then this one here we have 3, okay, and then we left with 2 3, we have taken out 2, therefore this is a square here. And then after that we have this 2 over 3 t cube, and so on and so forth. All right, so I hope that is clear at this point. Okay, now a lot of you at this point will be wondering, how do I actually obtain the summations for this infinite series here? Okay, now we need to recap a bit here. Okay, now from the normal geometric geometric summation or geometric series, for instance, xn, I just use a typical xn here, from x equals 0 until infinity, for instance, that is basically 1 plus you have x1, x2, x3, and so on and so forth. Okay, now that's how the summations look like. Now, if you try to differentiate this, okay, if you try to differentiate this, we will get n x n minus 1. So if you try to differentiate this with respect to x itself, okay. Now, by differentiating this, okay, indirectly we are getting, if you differentiate this, you are indirectly differentiating this. We are actually getting 2x, 3x squared plus 4x cubed, and so on and so forth. All right, now just to convince you that that is true, I need to add on one more term here. You can see that this is actually x4. So if you differentiate that, you get this. And then you would quickly notice that this series here is very similar to this one here. So this series here is very similar to the summations here. So therefore, you will notice that the differentiations of this is actually given by this one here. And then we already knew the summations for this, the summations of geometric series, which is actually one. Now, in this case, the infinite summations is actually 1 over 1 minus x here. So if we were to differentiate this, okay, if we were to differentiate this, at the same time you have to differentiate both sides. So by differentiating this, you get negative. Okay, let me see, do I get it right? You will actually get 1 minus x squared. You actually get 1 minus x squared there, right? Okay, so I hope that is clear at this point. Okay, so the summation of this is actually given by this formula here. And then in our case, the summations would be, so you can see that here is 1/3 square. So this whole thing can be written in this form here. Now that would be 1 over 1 minus, our x is this term here, 2 over 3t square. All right, and then there you have it. Of course, if you like, you can we can simplify that. So take for instance, if I simplify that, multiply by a 9, for instance. So if I multiply by a 9 here, there will be a 3, and then 2t over 2 there. All right. Now I hope this part you are clear with that. We are making use of the summations of geometric series here, which we have here. If you are going to differentiate the left-hand side of this, so if you differentiate this, okay, I'm going to write down the arrow there so that you know what's going on. So if you're trying to differentiate that with respect to x there, we are actually getting this power series. By differentiating this, you must also differentiate this section here. Okay, so differentiating this to this we will get this. So therefore, the summations of the power series, which is similar in structure to this, is given by this, where the x is actually 2 over 3t. That's how we get the summations of this power series. Okay, and then from here, we're going to finalize what they want us to do here. Now from here, I can actually write down as 3 minus 2t here, to the power 2. All right. And then now, if you notice that the gt that we have obtained previously was t over 3 minus 2t. And then therefore, that has provided us with a clear proof that this is actually the square of the probability generating functions that we have obtained in our first sections there. All right. So I hope that is clear at this point. All right. Now I'm going to move on to the last section shortly. But anyway, the last section is quite easy. It just require a bit of explanation here. So I'll just quickly explain that. That is a tree here. So explain why the probability generating functions of the number of shots until she hits the goal for the k time is equal to this. All right, because the total number of shots. Okay, so the probability generating functions for the total number of shots until k number of times. Okay, now I'm going to write it down here. So for instance, total number of shots of x1, x2, and so on and so forth until k number of time is actually given by, so the probability generating functions of the sum of the shots until she hits the goal k number of time is given by the product of the individual probability generating functions k number of times. So which means this one you multiply it by one time, two time, three times, until of course k number of times. K number of times. So if you multiply by that k number of time, so therefore we have gt raised to the power of k there. So that's the reason why we can say that the probability generating functions of the number of shots until she hits the goal for k number of time is actually given by the probability generating functions of t raised to the power of k, because the sum of all the probability generating function is the same as the products of the individual probability generating functions. Okay, so we are just trying to make use of the last properties of the probability generating functions for the sum of independence variables. All right, so that conclude the whole topics of probability generating functions. Okay, so I hope that is clear. Don't forget, click subscribe and then turn on the notification bell so that you can receive the latest video there. Right, until you see you guys again. Take care, everyone.